From now, we will see some Verilog design example. We will see and learn about how to do the hardware description language coding. So for Verilog, there are three different levels of description methods. One is behavioral description. This is just ready for simulation. So high level behavioral description can be done to test your algorithm or the functions. The register transfer level is a little more detailed. It is more closer to the actual hardware. So the RTL is like it is describing in a way to show that what is register, what is the logic, right? You can easily identify from the RTL code. So using that RTL, we can still simulate and do the gate level synthesis. We can provide that RTL code to the tool and we can do the synthesis and place and route kind of thing. The gate level description is composed of all the gates. You're describing your Verilog using the NAND gate, NOR gate, or the exclusive, or all kinds of logic gates you can use to describe your function. So as you go down, it is becoming more difficult for human being to understand what is going on. The easiest level for understanding is the behavioral description. It is written like a C language, any high level language, right? Very similar to that. But if you go down one step down, like RTL, it becomes like a flip-flop and combination logic, something like that. So it would be difficult for someone who is only did with the C language or MATLAB or something like that. You must understand how the hardware digital circuits are working to understand the RTL and gate level description. This is a simple digital design flow. First, you provide RTL register transfer level Verilog. So you may provide behavioral code only if such behavioral code is synthesizable. So there are two distinctions there. You can write a function, but sometimes it cannot be implemented in real hardware. So you must understand what can be done and what can be implemented. Throughout this course, we will see that. A gate synthesis is like a synopsis tool. They provide the design compiler to take the RTL Verilog code and provide the gate level netlist. The Cadence provide build gates, different tool. You can use that too. So anyway, starting from RTL, you generate the gate level Verilog, and using that gate level Verilog code, you can do the place and route. Actual layout cell can be placed, and also routing is done. So whenever you make interconnections, so the tool will do that for you. Not only just connecting the cells using wire, they also check the timing between the cell, considering the wire resistance and capacitance. Synopsys provide the IC compiler and Astro and Milky Way kind of thing. So Synopsys PNL tool. For PNL, Synopsys provide the IC compiler tool, and Cadence provide the SoC encounter. Every generation they provide different tool name, but basic operations are very similar. You go through the required step, but using different command for different vendors, but the concept itself is very similar. Once you do the place and route, you get the final digital layout. But when you do the place and route and also design compiler, you need the design constraint that the actual designer, digital designer, need to provide such information to the tool. For example, the clock speed and the logic delay for a specific path, that is, and clock skew and input delay and output delay and maximum transitions, all kinds of the constraint you can provide. Once the tool gets such constraint, they try to synthesize the block, trying to satisfy such design constraint or requirement. The Verilog starts with the module definition. Here is the Verilog example for defining module. So starting with the module and end module, there the name of the cell. We're trying to implement the 2-to-1 mux shown here. So out is cell and A or cell bar and B. This is the conventional, the 2-to-1 multiplexer. And you may also provide the inverted value. So this block starts with the module and the name of the module here. Now you describe all the input and output ports. So we have input A, B, and cell, and output out and out bar. So 5 signal, 1, 2, 3, 4, 5 signals are defined here. The double dash is the comment, and then we define. So not only we define the ports here, we also need to define what kind of port you are using. It can be input or output, right? The input A, B, cell. You need comma there between to separate all different ports. Once you define the input and an output, now you describe the behavior. By default, you can use the assign statements here. Out is assigned. If the cell, we have a special keyword question mark that is same as if statement. So if cell equal to 1, then out is A, else out is B. This is the same statement as the if statement. So if the cell is high, then we assign the A to out. If the cell is 0, then we assign B to out. Here we use the assign statement here. So assign statement only can be used for wire definition variable. Wire definition. So we want to use that to use for assigning wire definition, assigning some logic to wire definition. So meaning in order for the assign statement to be used, the out signal must be defined as a wire. So by default, if you don't specify any wire characteristic, then out is defined as signal wire. So here, input signal and by default defined by the wire signal. This is the property of the signal type, and out is also a wire. Yeah. So input and output, if you didn't specify the wire type, the signal type, then by default the signal type is wire, so you can use that assign statement. So another assign statement, out bar is assigned by the out tilde. Tilde means the inversion. So out inversion of the output is assigned to out bar. This is the end of the description for the 2-to-1 multiplexer. So here you have written two statements here, 1 and 2, two assigned statements. What's different from the conventional C language or other the programming language? The hardware description language like Verilog execute all the lines at the same time. So because that's how the actual hardware works, right? Even though you wrote like this, those two lines are executed or evaluated at the same time. There's no difference whether you move this assign statement to the top, right? There's no distinction of the assignment statement order. So all the statements executed in parallel, so concurrently executed. This is the actual hardware, right? It works, how the hardware works. This is different from the conventional program language. Now we have to be more careful about the assign statement here. So we use the continuous assignment. So assignment keyword using the assignment. This is the simple just way of representing the combination logic. You can do like if you wanna describe like A and B and out, then you can write that assign out equal to A and B. And B, right? Something like that. So you can use your assign statement to represent the combination logic. So conceptually, the right-hand expression here, shown in here and here, is are continuously evaluated. Meaning, whenever input A and B or cell changes, it evaluate and update the output, right? Any input changes, such statement will be evaluated, just like a data flow. So by having assign statement, we are generating wire net driven by the combination logic, right? You have to keep in mind that wire, the assignment is done is happening on the net or wire. The left side of the assignment here should be wire type or net or scalar or vector net. Any net type or wire. You cannot use register, the scalar or vector register. So you can see that there are two types of variable you can use in the Verilog. One is wire or net. Second one is register. Register is the variable that used in special types of the signal. This doesn't mean actual flip-flop. This does not always mean it's a flip-flop. It includes more than that. The register can be actual wire. It can be implemented wire as well. It can be actually implementation can be wire or flip-flop. Why? What the heck? Why we are using when we require such a register definition? The register definition is required if you want some operation in sequential way, like a programming language. You want describe the behavior sequentially, then we have to define the signal in register format and use that signal assignment inside the always statement. So we will see that always statement later. For now, we are focusing on the wire. We are dealing with the wire only. The net assignment is always done by assign statement here. So we learned about the conditional operator, like a if statement. So conditional expression is satisfied, then this value is selected. If not, if false statement is there, the value on the right hand side, that will be selected. There are the Boolean logic like tilde, ampersand, and bar and hat. Arithmetic operator like a plus and minus are also possible. For the conditional operator, you can nest it. So there can be multiple if statements. For example, S1 is true, then inside here we can add another the conditional operator here. If that S1 is false, then we can check another the conditional operator statement there. So we can nest the multiple nesting conditional operator can be possible. Okay. And now we'll look at the procedural assignment, different from continuous assignment. For the procedural assignment, we use always statement. Procedural assignment allow the sequential execution of the line. There's some order. Actually, the order may matter. So different from the continuous assignment. It is like a C language, like the operation. So it allows the behavioral description of the combination logic, and also higher level. This is like a high level of description. There are two structured procedural statement, the initial and always. The initial statement is just provide the initial condition for any variable, but for the always statement, typically we use for actual logic design. The initial statement cannot be implemented in hardware because the behavior of the initialization cannot be done just by defining using that initial statement. It must be some hardware driven reset should be used for initializing the variables. In the previous example, we looked at the multiplexer 2 to 1 mux. We can also describe that the 2 to 1 mux using always statement. So we have a module definition here. So input port definition, this is same as before. The difference here is we added like a register definition, out and out bar. So output is defined by the register type. This register type doesn't mean actual this is a register. This means we are gonna use that variable for using the procedural assignment. That's the way how you declare that type. So something that defines the register type must be used inside the always statement. So here always statement start with always and begin and end. So here ampersand, after ampersand you specify the sensitivity list. This is the sensitivity list, meaning that whenever this A or B or cell changes or any logic transition or variation will start evaluate this inside the always statement. So once the A or B or cell changes, then we go inside and try to see this sequential, this procedural statement. This is like if cell is satisfied that output is assigned to A, output is assigned by A. If not, output is assigned by B. Now the out bar is equal to tilde out, so out bar right there. So you can write it like in this section. You can still write the out equal to cell conditional assignment, like a cell question mark A and B, like that. Then out bar equal tilde out, right? Something like that. You can change that. You don't need to use if. You can use that conditional the statement like a question mark. Now the big difference is that inside the always statement you cannot swap the statement, because if you cannot start with the out bar, because the out bar is assigned by tilde out, so inversion of out, but out is not yet defined, right? If you execute this one first, so that is not allowed, right, for procedural assignment. So you have to first describe this section, this line, or if here, if statement, the first if statement here. In that way, the out is defined, right? And then we execute out bar equal to tilde out, right? So the order actually matters, right? The procedural assignment. This is very important. You have to remember. Okay? The statement is sequentially executed from the first line to the last. Okay. The inside the always block, multiple statements can be possible. You can define the out and out bar, or so you can add another multiplexer like out2 assigned by cell 2 question mark and C and D, and out2 bar equal tilde out2, something like that. You can define multiple action. But the one thing that you also remember is that even though the execution is done sequentially, the actual hardware is exactly same as the previous continuous assignment. This behavior is interpreted like a conventional combination logic. So this is how the tool interprets the variable and how how to evaluate the provided statement. To summarize, we have a continuous assignment and procedural assignment. For continuous assignment, you use assign statement, right? And for procedural assignment, you use the always statement. Okay. So we need to understand then the register definition in Verilog. It is a little different from what we know from this course. And typical digital system register represent the memory elements, right? So digital register require clock. So this is like a flip-flop, right? Flip-flop require a clock to operate and update their state on a certain phase or edge, like a rising edge or falling edge. But in registered in Verilog is defined differently. You never confuse with the actual digital registers. Registers in Verilog is not actual hardware register. In Verilog, the term register just simply means a variable that can hold a value. Why we need this kind of definition in Verilog? By having this kind of definition, we can assign the value in sequentially, like C goes to let's say A goes to B and B goes to A, like in this kind of so let's say A goes to B, B goes to C, and C is assigned to D, like that, something like that. So you need to evaluate D, variable D, you need to evaluate this first line and then second line and third line, like in this kind of a sequential order. To do that, the value need to be stored. I mean, we have to remember the value that's stored here and then use that value and to assign that B to A, like that, D to C, something like that. So this register in Verilog just means a variable that can hold the value, and also this kind of a sequential description must be inside the always statement, right? Inside the always. So Verilog register doesn't require a clock, and also it doesn't need to be specified like a driven like a net, right? So value of a register can be changed anytime in simulation, like whenever you assign new value to that variable, you will immediately change the contents. So registers definition in Verilog is different from digital registers, right? You have to understand. We will see some of the example throughout this chapter. So when we describe the 2-to-1 multiplexer here, we can mix continuous assignment and procedural assignment. We can mix those two kinds of the description method. For the multiplexer, we can use the always statement, like a procedural description. And for the last out bar, we can use the continuous description like that, using the assign statement. Those kind of mixing is totally fine, because the Verilog description language is representing the hardware. They're representing the same hardware. You can either describing it in procedural assignment like always, or the continuous assignment like assign statement. No problem. But what you have to remember is that in procedural description, you must define the variable that is being assigned. For this case is out. Out must be here, out and out bar, so here, I'm sorry, out here must be defined as a register like that. You must define the reg out in the beginning. So otherwise it will give us the error message. The tool cannot compile. But in always statement, you must do not miss this sensitivity list. To evaluate the out variable, input A or B or cell must change. If those input doesn't change, the always statement will keep the same value. The out will be the same as before. So if you miss to describe that cell in here, if you omit that cell or B, one of any input, then your function will not work properly. In that way, some assign statement is easier for you guys to describe because you don't need to put the sensitive, you don't need to describe any sensitivity list like always statement, because by default the assign statement always evaluated whenever the input side, the right hand side assignment is changing, then always it automatically evaluate. But the always statement, it must satisfy the condition described inside the sensitivity list. This is very typically the many student or engineer make a mistake for filling out this the sensitivity list. Case statement. So case statement can be used to replace the if statement, but case we can, by having case statement we can define more complicated conditions. So case is much more easier to read than a long string of if-else statements. Many if-else statements inside, it will be difficult. So here example, just we are showing just a single bit control, like a cell signal shown here. The if statement like this, if cell is high, then the output is assigned by A. Output is assigned to A here. But in describing in case statement, you can obviously see that if the cell is 1, then out becomes A. If the cell is 0, out becomes B. Like you can see it, you can watch it very clearly in the description. For example, if the cell is multi-bit, like a 4-bit, you can describe the 000 cases, 0001 case, like all the different cases you can specify like that. So it is much easier to read for identifying what is going on. But the problem here, the one thing that you must understand is that case statement, when you specify the case statement, the case should be exhaustive, meaning that you should not miss any cases. You have to describe all the cases. For example, you described only 000 cases and 0010 and 1111 cases. So there are so many 2 to the power of n cases, but you only specified like 3 cases. Then it will give us more trouble. You have to specify all the cases. For the missing cases, you can use some default cases. When anything that doesn't goes to any of these category, then go to default statement. You will see in the next slide more detail. Gate level discussion is a little different from what we had. So previous case we had the RTL describing like this kind of a 2-to-1 mux. But in this case, to represent this AND gate, OR gate, and inverter, This kind of gate level description can be also done, but it is very difficult for human eyes to identify all these gates corresponding to multiplexer. It's almost impossible. So this kind of description is usually used after digital synthesis. The synthesis tool will take the RTL code that we had written before, and then it will spit out this kind of the CAD tool will generate the gate level description like this for the place and route operation. The Verilog naturally support the basic logic gate as a primitive, for example AND, NAND, or NOR, XOR, XNOR, not buff. Primitive means even though you don't define its function, internally it is recognizing that it's AND or NOR. So this is the predefined the logic function. So AND, not AND, or something like that. That's something that you can use for gate level. This kind of the logic gate can be extended to multiple inputs, like a 3-input NAND 3-input. If you specify the output, this is the output, and specify the input like that, then it will automatically recognize the first one is output and rest of them is the input. Buff IF1, buff IF0 is the tri-state buffers, something like that. So you can use many definition of a primitive function. But mostly, personally, I don't have any experience for using such kind of a gate level. The only time you see the gate level list is only when you debug your place and route result. So from the synthesis tool, it will generate gate level list. You will try to see inside and trying to understand what is going on, or sometimes there's some error. The node net name, the capital and small letter and uppercase letter that are generated in one tool, one CAD tool recognize those upper and lowercase letters, but some other tools cannot recognize those cases. Sometimes that causes the errors in the actual simulation. So the only time you see this gate level description is mostly when you debug your design from the synthesis tool. So all the net you specified here defined by the wire, right? So this is kind of optional, even though you doesn't define like a wire function like this. Nowadays the tool recognize that by default out1 and out2 and cell bar, like the signal that you used for like interconnection, is internally defined by the wire. So this is the keyword. The wire net definition keyword is wire here. This example shows that n-bit bus signal. So for the multiplexer, you may take in the 8-bit A and B. So same function for multiplexer like this. So you define the 7 to 0 with a big bracket like the scale bracket. Using that, you can use that the bus representation. This bus notation should be defined between input and variable. So register is also same. You put it that the number of the bits representation inside between the signal type and signal name, and then you specify the same way you did for 1-bit multiplexers. The out bar and tilde, all the bits are inverted like this. Sometimes you may concatenate the signals, so you use like a curly bracket operator. For example, if you want to assign B7 to 0 signal, the B is 15 to 8 signal that assigned by this A15 to 8, A7 to 0. You can change the connection, the bus, the location by using the curly bracket operator. This concatenation using curly bracket is a very useful operator you can use. So integer arithmetic operation example is shown here. So we have a module definition of a 32-bit adder. So you take in 32-bit A and B and you generate the 32-bit sum. So input defined by 32-bit, 31 to 0, A and B, and output is also defined like that. Since you haven't specified the signal type here, it automatically recognizes that as a wire or net. And for the net assignment, you use assign and sum equal to A plus B. So you add that value on, this is unsigned addition. ADITION. Then you get the 32-bit plus 32-bit sum is the on a 32-bit that goes to assign to sum. If you want to represent the carry in and out, so you can use the concatenation operator so that the output is total. This is 33-bit because 1 plus C out is single bit and sum is 32 bits. So total 32-bit output is assigned by A plus B plus C in. Then you can have the final, the C carry out signal can be also, you can get by having this kind of assignment. Okay, this is 32-bit plus 32-bit plus C in is 1 bit, right? The total 32-bit output is assigned to C out comma sum, right?